Concepts to kind of set the context, and then we'll, since this is a tutorial, I'll try to do some code walkthroughs and some demos and explain things with some numerical examples so that you're able to take away something that you can apply in your work. Okay, so what is audience segmentation? I'm going to be talking about that as the first thing, introduce the topic. How is it relevant to our pay-TV business and with respect to our value chain? And what is the current state of the art and what challenges do we face in implementing audience segmentation? And after that, we'll do a deep dive of some advanced data science concepts and how we can apply that to audience segmentation. And then from theory to practice, how do we roll out a feature that we can monetize and sell to a customer as part of Bento? So these and some updates as to the roadmap and the future plans will be discussed towards the end. Okay. Let's get started. So Wikipedia says that they have it. Audience segmentation is about identifying people into subgroups of people, and you do this based on many traits like product usage, demographics, psychographics, communication behaviors, and media use. This is, I think, a good summary of what this concept is all about. Wherever you have an audience, be it online or be it pay TV business, you would like, if you're a content creator, if you're anybody in the value chain, service provider, channel operator, you're interested in knowing who your audience is, how are they consuming your content, what devices do they use, what location are they situated in, etc., and so on and so forth. So this is a very important feature that many people are asking for. So these are all the parties involved in the value chain or the ecosystem of pay TV business. At a very high level, I don't want to get into too much of detail and spend time on this slide. Everybody wants to know who the audience is, what is the composition of a household, what is the content that they view. And this is very important for doing something like targeted advertisement. Advertisers are constantly trying to reach out to a niche market, a specific market for their products. People are also interested in gauging, like you're all my audiences, and I'd like to know what is the distribution of people, what are your profiles, how many of you are engineers, how many of you are managers, product managers, and what do you plan to take away from this. So I'm interested in positioning, if you will, this presentation in your minds and trying to understand, gauge your feedback. Imagine how industries which create products and services would be much more interested in gauging how the audience is responding to their products and services. So brand managers are interested in this. Channel operators are working closely with advertisers, and they've taken ad spending dollars. So they'd like to justify it, saying, we promise that your ad would be shown to so many people of this particular demography in this location. We've met these numbers. So this is a very important part of the whole ecosystem in order to make it work. So you might ask, how is it currently being done? Well, you have certain audience measurement agencies put together by, it's a conglomerate of so many agencies. Some of the industry leaders in pay TV business have joined with some of the private parties or with the government agencies, and they put together these organizations like BARB in the UK, which is Broadcasters Audience Research Board. And what they basically do is they create a small sample size of about 5,000 to 6,000 households, and they collect data. They instrument the customer premise equipment, and then they collect the data. They denoise it and extrapolate all the interesting patterns, and then they give it and they sell it. Actually, Nielsen is into this business for online as well as pay TV business. They sell you the data and the summary reports, and it's not inexpensive. It's quite costly if you want to tie up with these people. And there's also this aspect to this whole process that although there are some government parties involved in this, you don't know how much of the data is made to fit certain expectations as opposed to revealing the real trends and patterns. And also, if you look at 1 million households in the UK, approximately, which is your subscription base for B-Sky-B, and if your panel is only about 5,000 to 6,000 households, you're looking at a sampling error or extrapolation error you cannot possibly make very broad sweeping generalizations for the entire census with a very small sample size. Any other approach like sticking a camera in the living room of people trying to find out who's watching TV, etc., is frowned down upon, infringes on privacy, not a good thing. Then service providers actually, they build this ecosystem, the entire backbone on which this ecosystem is flourishing as far as technology is concerned. They have access to analytics data. They're sitting with a minefield of, a gold mine of data, and they want to basically see what aspects, what interesting patterns can be extracted from this. It's a big data problem, and many of them are kind of lost. We have the data. How do we get it into a form where we can extract interesting patterns? That's the question they're asking. Then there's this other thing about the primary account holders. Service providers have a lot of data, but then this only pertains to the primary account holder in the household. And there's a problem with that. So you just have this gentleman here on the sofa, and he's signed up for the service. There are some people sitting next to him. You don't know anything about them, and all the conclusions that you would make about the viewing in the household would be attributed to this person. He's a male, probably between 30 and 40, high-income group, lives in, blah blah. But that's not really going to help. In fact, it's going to be disastrous if you make any assumptions based on the primary account holder. So what we attempt to do as part of Bento, and Bento, all of you, is a cloud-based pay TV solution. It's a mixed bag of services. Feel free to pick and choose what you want, or take the whole lot, deploy it, and you can be up and live very soon as a service provider. We are going to demystify this and answer those question marks in the first image. So we're going to put a face to the people in the house. And then we're also going to get you more fine-grained details, descriptive tags about who these people are, what do they really watch, what are their demographic characteristics, etc. So fundamentally, this is a problem statement. I might have to skip through a few slides in the interest of time. So the problem statement is this: given the aggregated viewing data for a household for a time window, can you extract information about the number of people in the household primarily? And secondly, what can you tell about their demography details? What can you tell about their viewing preferences? So this is kind of a very high-level problem statement for us. All right, so as it so happens, we have a solution which is already rolled out and ready to be deployed as part of the Bento release in January. We have a trial lab-to-lab collaboration with the customer in France, which is Bouygues Telecom, and that's an ongoing activity as well. We have a business intelligence dashboard which looks somewhat like this. Of course, we have newer, updated versions of the same thing, but more or less this is how it looks. So what you do is you select a particular household, and then once you've done that, on the left-hand side you see a cluster of points. These clusters represent specific viewing activities for the household, and that's for a particular tenant. In this case, it's Bouygues Telecom. And then the number of clusters is mapped to the number of people in the household. And as you throw in more and more data, the delineation between people's viewing characteristics starts becoming more evident, and then you can precisely lock on to how many people are actually watching TV in the household.
What do the data points represent?
Each data point represents a viewing activity, and I'll actually show you the data format in the next slide.
Okay.
You show us how you get this data?
Sorry?
You show us how you get this data?
Yeah. And on the right-hand side of this business intelligence tool, which is built using Pentaho, you see certain bar graphs. They represent both the demography details. The person is probably a male in the age band of 30 to 40, etc., etc. And then you also have descriptive tags like ESPN lover or music lover, etc. And I'm going to talk about how we build various elements of this particular solution, and you'll be surprised to know that there's quite a lot happening in the background. There's some unsupervised learning, which gives you the clusters. Then you have statistical modeling, which gives you some ideas to who those people and what their demographies characteristics are. You have a knowledge-based system or an expert system which fills in the details about the descriptive tags for each person. All right, so before I address the exact data format, I wanted to go some things. Here begins our deep dive for the data science topics. Some of the tools that we use, basically the way we do this is we prototype using MATLAB, R, SciPy, etc., and then we go into production using Mahout. Mahout plays very well with Hadoop, and so we are married quite closely to Hadoop family of products as far as deployment is concerned. So we take Mahout, which gives you the machine learning capability on top of Hadoop. First of all, let's talk about the data. I'll give you the insight into how the data is acquired and how we process it and how we get it into a form which can be fed into Mahout. There's a difference between the human intelligible form of data and what Mahout understands, so I'll tell you how the transformation happens. Then there's a concept called PCA. I'll get into details as to why we need it. And then I'll give you an overview of the supervised and unsupervised machine learning algorithms used. And there's always an element of benchmarking and iterative refinement of your algorithms whenever you work with data science. You don't get it right. You'd be very surprised if you get it right in the very first shot. So there's something called cluster analysis which we're using. We use that. We get that to tweak our algorithm and make it work better and faster. And I'll explain how we do benchmarking for this. And all the customers are interested in not just the result, but also your benchmarks. So when we go to market, and we are going to be competing with many industry leaders in data science, so we need to benchmark our algorithm and our process. And this gives us a lot of increase the confidence in the mind of the customer when they engage with us. Then I'm going to be talking about something called a guidebook of prior probabilities for each content and how we use it to build a statistical model. And then we have a demo component for all the three elements, so I'd like to spend more time on the demo and code walkthrough rather than talk about it. Okay, so here's a glance at the data. This is actually real data which pertains to a particular household of somebody living in France, so it's not made up. There are timestamps. You wanted to know how the data arrives, so we collect it as a bulk ingest, as usage logs or usage reports from the customer. We provide an endpoint in the cloud where they dump the bulk ingest, and then we start ingesting it. So this could be a time window for a month or for a week, or we leave it open to the customer to define that. So it arrives at our doorstep for a particular window of time. I've just taken a small snippet of it, a microscopic snippet of it. These are all viewing activities for a household. They come in as actions. So channel surfing and sustained viewing are mixed up. So we filter out all the channel surfing. If you just tune to a channel for a couple of seconds, you didn't really watch. We filter out all those things as a pre-processing, denoising step. Then these are all chronologically listed, and then you have channel ID, genre, time bin, day of the week, and content name. These are relevant and important for us as a data mining exercise. So we made a call, and when you have so many features, and we had to limit it and say, we don't need so many. What is the most relevant that we're interested in? Surely the channel that somebody favors, or the genre that they favor, or the programs that they favor, these are all interesting aspects of the data model that we want to mine. Do you really care about whether somebody watched a particular episode in a particular season of a particular TV series? Not really. That level of granularity doesn't really help, because the fact that I watched season 10 of a show, but I missed season 9 and I watched season 8, doesn't really help us distinguish like one individual from another. So if you get the content name, in this case, I think there's some TV shows like House, Dr. House, something. So if you have the content name as a TV series at a high level, that's good enough, which is why we've dropped ISAN number, which is a unique number for international number for any TV series, and the season and the episode information. So the highlighted regions are the ones which are now going to be information rich for the next stage of processing, and it is a pipeline. It's a machine learning pipeline. We've just started at the head of the pipeline. Let's first understand how this raw data comprising of these 5 columns gets converted into feature vectors. And we have to do this because this form is human intelligible, whereas the form that goes into Mahout is not human intelligible. It's a bunch of vectors in vector algebra representation. So data is usually of categorical or numerical types. All the data that we're working with, the 5 columns or attributes, are categorical string data types. And we've applied some domain knowledge. We didn't pick them at our own whim. We applied some rationale to it. So it requires some domain knowledge. But there is a possibility that they could have interdependency or correlation. What do I mean by it? If you watch, let's say, action movies only, and BBC telecasts action movies usually between 8 and 10 in the evenings, it stands to reason that you predominantly watch TV only between 8 and 10 in the evenings. So there is a dependency between the time of the day column and the genre being action. And we have to factor such things into our equation, otherwise you'll be working with a lot of features which have a lot of dependency, interdependency, and a causal model. And machine learning algorithms don't perform that well when you have a lot of correlation and interdependency. You have to somehow remove it. The next subsequent slides will talk about how we, after denoising, how we make these columns independent. Okay, so here's a hello world example, my first numerical example, to explain how this works. So take a look at this weather data. You have 3 attributes: outlook, temperature, humidity. You can immediately relate to the 5 attributes that we started off with our pay TV domain. So this is to give you a parallel in another domain: outlook, temperature, and humidity. Each of those can vary in 3 ways. So you're now left with 3 attributes with possibly 3 values per attribute, right? And you would notice something that here I sorted them lexically in a lexicographic manner, all the attribute types, and the attribute values for every attribute type is also lexicographically sorted. And this is important for the algorithm which follows, which is called one-hot coding. What it does is it creates a vector representation for each of the attributes. Only one possible value in this particular vector can be turned on. So you go look up 9th December and you see that the outlook or humidity is high, and high happens to be the first position in this vector, so you turn that vector on, 100. You repeat this exercise for outlook and temperature, and then finally you flatten it out, and this is what you get. So this is the vector representation that Mahout needs done. You have to normalize it also, because all these machine learning algorithms use distance metrics like Euclidean, cosine, and there are about 15 to 20 distance metrics which operate in a hyperspace, which is a unit hyperspace. So you want all your data to be normalized. By normalize, what I mean is, if you were to square each dimension of this and add them up, it will add to 1 unit length. Okay. So I've not filled the rest of the grid. We can work on it if time permits later. Is everyone with me on this? Okay. All right. So now we've converted raw data into feature vectors. Let's talk about some problems. The features may not be independent. That's something we already talked about. Attribute relevance. People can split hairs about whether one column is relevant or one attribute is relevant or not. So some kind of a domain expert has to help in this process. Then there's a visualization challenge. Suppose you have 5 dimensions. Let's forget 5. Let's take 3 dimensions. Let's take content name, time of the day, and day of the week. How would you plot this and visualize it? We are all capable of 3-dimensional visualization, up to 3-dimensional visualization. So in 2D or 3D, how would you plot, let's say, content and genre? It's very difficult. In fact, it's a very big challenge for visualization because we're used to Cartesian coordinates, x, y, and z axis. So the moment we have some other space, we're unable to fit that into our Cartesian coordinate. We can't visualize the data. That's where PCA comes in handy. This is a statistical tool. It helps in, you can basically, the way PCA works, very simply put, is it looks at all the data, finds out, first of all, the very first axis along which the data is squished. You can see that there's a force being applied from here and here, and it's squished. So the variance extends diagonally in one direction. That's your first axis. The first axis also happens to be the primary axis along which you capture the maximum variance in the data. You can see that there's another black line here, that is your secondary axis, and so on. How many axes do you have? You have as many axes as you have columns in your data. What's nice is all the axes are orthogonal to each other, 90 degrees, so you can actually visualize them quite well. Another nice thing is it's domain agnostic. So whether you do audio analysis or image processing or pay TV related use cases, it doesn't matter. You can be a statistician who can come in, apply PCA, and you'll be able to visualize the data. It's not just for visualization though. What you've actually done is you made all the columns independent, and that's a prerequisite for many algorithms like naive-based classifiers. Another nice thing is it rank orders all the components. So the very first component is the information-rich part. The second one is second and most information-rich part, etc. So what it means is empirically they found out in many examples that even if you have what is the length of our vectors? I think it was nine-dimensional, right? We have 3 attributes and 3 values for each attribute for our weather hello world data, and we ended up with a 9-tuple vector. Tuple is just another name for dimension. And you can see that as you add more and more features, and the more, suppose in a month you watch totally 200 unique movies or 200 unique content names, entries, then you would have a 200-tuple vector just representing one attribute. So you can very easily see that this explodes quite out of proportion very easily, very quickly. But PCA tells you that if you plot the variance after a particular point, it starts plateauing. So after the 4th or 5th principal component, you can actually truncate and leave the rest out. It gives you tremendous amount of boost in terms of computing power. You don't have to look at 1,000 or 2,000 tuple vector. You just have to look at the first 10 or 15, and 95% of the variance is captured through that. Okay, so PCA for Buick, this is an actual deployed model that I'm bringing up. It's not make-believe data, and you actually see that for that particular household, this is how it looks. We've actually predicted correctly that there were 3 individuals in the household, and I'll tell you what I mean by predicting something correctly in this case in just a moment. Cluster 1, 2, and 3, and the data is color-coded. Of course, this is a